Lesson number 27, Daily Summary. In this lesson, we begin our work with algebraic fractions or rational expressions, including simplifying them, multiplying them, and dividing them. Number 1, here are some examples of algebraic fractions. 5 over x squared, x over x plus 2, and then x squared plus 5x plus 4 over x squared plus 6x plus 8. What makes these algebraic fractions and not just ordinary fractions? They have a variable in them instead of only constants. We can evaluate, simplify, and perform operations with algebraic fractions just like we do with ordinary fractions in arithmetic. So we're going to review some ordinary fraction arithmetic in order to extend those same principles to the fraction arithmetic of algebraic fractions. In arithmetic, we are asked to simplify or reduce fractions to lowest terms. Here's how we can reduce the fraction 24 over 54. So the short way is to just say, well, 6 goes into both of these numbers, right? And so if you reduce them both by 6, divide them both by 6, you get 4 over 9. And that's it. We're going to write this out a little bit longer because I think it's going to go somewhere useful. So we rewrite 24 as 6 times something. In this case, it's 6 times 4. And then 54 also as 6 times something. It's 6 times 9. Then we're going to separate this thing out, and we're going to make two different fractions multiplied. And that is, this equal sign right here should be reasonable, because to multiply fractions, we know we just multiply straight across, which after all is exactly what's written over here on the left. And then 6 divided by 6 is just a fancy form of the number 1. And then 1 times 4/9 obviously is just 4/9. So yeah, sure, we could just divide top and bottom by 6, which is normally what we would do, like up here. But really what we're doing is pulling out a fancy form of 1 and then not writing that fancy form of 1. In the above calculation, we can cross off the 6's because 6 over 6 is just a fancy form of 1. We will abbreviate this as FFOO, which is hard to pronounce unless you make something up like Aaron Eisen did and pronounce it fufu. It sounds kind of silly. It doesn't quite look like fufu, but it's good enough. Fufu is going to represent fancy form of 1 for us. Number 4, are we allowed to cancel the 2's in these fractions? Well, let's take a look. 13 times 2 over 2 times 3. For sure, that is equal to 26 divided by 6. And then if I reduce that fraction, 2 goes into both of them. I get 13 divided by 3. Was I allowed to cancel the 2's? Yeah, because what I have left is exactly 13 divided by 3, which is the right answer. So yes, when you have multiplication on top and multiplication on the bottom, you are allowed to cancel common factors. Let's take a look at part B, which is similar to part A. It's just addition instead of multiplication. All right, for sure, the right answer here is 15 divided by 5, which is just plain 3. If I were allowed to cross off these 2's, what I see there is 13 divided by 3, which is definitely not the right answer. Right answer is 3. Maybe you cross them off and you put 1's on both instead of the 2's. You put 1's. 13 plus 1 is 14 divided by 4. That is for sure not 3. So no, you can't cross off the 2's, not in any way. So you can't cross off 2's when there's addition, even though it might seem reasonable. It might look like you can. Same deal for subtraction. The right answer here is 11 divided by -1, which is just -11. Is there any way to cancel those 2's and see the answer of -11? So that to me looks like, I don't know, 13 over -3 maybe, if we cross off the 2's and put 0. If you cross off the 2's and put 1's, 13 minus 1 is 12 divided by -2. That's not -11. So no, you can't cancel there either. Number 5, based on the examples above, we should see that we can only cancel when we have multiplication. We cannot cancel when the main operation is addition or subtraction. So no matter how tempting it is to cross off 2's when you have something like that, you just can't do it. And to cross off 2's here, you just can't do it. Only when you have multiplication are you allowed to cross off those common factors. All right, so the main idea in number 6 here is to simplifying or reducing algebraic fractions is to look for common factors in the numerator and denominator. And if you have a common factor, then you really have a fufu, and you're allowed to cancel the common factor. So let's take a look at this first example. X squared minus 9 over x squared plus 6x plus 9. Our goal is to reduce this fraction as much as possible. So first question to you, are we allowed to cancel the x squareds? Second question, are we allowed to cancel the 9's? The answer to both of those questions is no, 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 because this x squared is next to a subtraction, and I cannot cancel unless it's multiplication on top and multiplication on the bottom. So you can't cancel those. And the same thing on the bottom. This x squared is sitting next to an addition sign. It is not fair game. Neither is that plus 9. It's sitting next to an addition sign. This 6 times x, I mean, that's multiplication. I guess technically even the x squared is multiplication, right? Fundamentally, it's x times x. But it is still sitting next to a plus sign. And so, no, we can't cancel anything there. What we can do instead is factor numerator and denominator completely. Let's do that. Big old fraction. Upstairs, we've got 3 kinds of factorings we always look for in the same order. Greatest common factor first. Greatest common factor upstairs is 1, so there's nothing to do. Second kind of factoring is the difference of 2 squares. In this case, on the top, there are 2 terms. They are both perfect squares, and indeed it is a difference, so it is the difference of 2 squares. So we get to do our short difference of 2 squares formula. So 2 sets of parentheses. X squared came from x and x. 9 came from 3 and 3. 1 plus, 1 minus in either order. That's our difference of 2 squares formula. And downstairs, we're going to try to factor that one now. X squared plus 6x plus 9. Again, same order for the 3 kinds of factoring. Greatest common factor of those 3 terms is 1, so there's nothing to do there. Is it a difference of 2 squares on the bottom? Nope, it's 3 terms. So then the last kind of factoring is the 2 by 2 box. So I will just hide the details and say, pause the video here if you want to, but ultimately we need to get the answer from a 2 by 2 box. So hopefully I've had some time to get the 2 by 2 box done, and we should have come up with x plus 3 times x plus 3. Okay, let's take a look now at the fundamental operation on top. Yes, there is an addition, and yes, there is a subtraction, but neither of those is the fundamental operation. Fundamentally, the top is a big, fat multiplication. The things in the parentheses have addition or subtraction, but the top is a multiplication, and the bottom is also a multiplication. Right in there, right between the parentheses. And when you have multiplication, you're allowed to cancel. That's what we saw with the 13 times 2 over the 2 times 3 up above. So we cancel common factors, anything that's a carbon copy on the top and on the bottom. And I see an x plus 3 and another x plus 3, and I cross them off, and it's reduced. And you might wonder, how come I can cross off the plus 3? Because there's addition, right? Why can I cross off the x plus 3? There's addition, and I said you can't cancel when there's addition. Yeah, but addition is not the fundamental property. The fundamental operation, I should say, is multiplication. And this entire x plus 3, I mean, they, kind of like blur your eyes a little bit so you can't see the details. It's a carbon copy of what's up here, and they're just multiplication. It's like a times 2 and a times 2, and then crossing them both off. So don't be fooled by the addition inside, and that is not a problem. Carbon copy, top and bottom, they can cancel. Okay, so what we're left with is on top, x minus 3, and on the bottom, x plus 3. And my question to you, are we allowed to cancel the x's? Are we allowed to cancel the 3's? And the answer in both cases is no. The stuff on top is not available to you because it's subtraction, and the bottom is also not available, it's addition. The only thing we can cancel is over multiplication. So that's why factoring first was the technique. Next page, 3x plus 2 over 6x plus 24. It's tempting to try to start crossing things off. 12 and 24 have a common factor. 3 and 6 have a common factor. Don't do any of that. It is addition on the top, addition on the bottom. None of it is available for crossing off. But what you can do is factor. So upstairs, greatest common factor first. Oh, okay, it's 3 here. And when we pull out the 3, we're left with x plus 4. Downstairs, it's 6. And we pull out the 6, and it's x plus 4. And now fundamentally, upstairs and downstairs are multiplications. And so I can reduce. I can cross off those x plus 4s. They are carbon copies. So I get 3 over 6, which just reduces like an ordinary fraction to 1/2. Next one, part C. 2 plus x over 2. Are we allowed to cancel the 2's? The answer is no. One of those 2's is ready to be canceled. The one on the bottom has no problems, but the one on the top is right next to an addition, and that is no good, not cancelable. So instead we factor up on the top. 2 plus x, greatest common factor of those terms is 1, so nothing to do there. Is the top a difference of 2 squares? Well, it is 2 terms, but they're not perfect squares, so no. And can you use a 2 by 2 box? No, it doesn't have the x squared term in it. So the top is not factorable. The bottom is just plain 2, not factorable. So this one can't be reduced, and that's the answer. It's okay to say something can't be reduced. It is simplified as much as possible. But what you need to do is avoid reducing something that you're not allowed to. So don't cross out those 2's. Number 7. Let's consider the algebraic fraction x minus 3 over 3 minus x. What is the value of this fraction when we evaluate it for the values of x equals 10 and x equals negative 2? Let's try 10 first. I'll do it over here. So I'm plugging x equals 10 upstairs for the x and downstairs for the x. So the same, x became 10 in both cases. 7 over negative 7 reduces to negative 1. Fair enough. Now we'll plug x equals negative 2 into the original fraction for both x's. Upstairs, negative 5. Downstairs, positive 5. Careful with the signs. Reduce, we get negative 1, which seems coincidental that we got exactly the same answer by plugging 2 different numbers in. We got negative 1 as the answer both times. And it turns out it's not a coincidence, and it wasn't anything special about x equals 10 or x equals negative 2. You can pick any number you want and plug it in for both of those x's in that fraction, and you will get negative 1 all the time, I guess, except if the fraction is undefined, but that's a minor detail. Number 8, in general, any fraction that has the form a minus b over b minus a is equal to negative 1. That's the form, right? X minus 3, 3 minus x. They're exactly the same. They're just like in reverse order, right? X minus 3 and then 3 minus x. So any fraction of the form a minus b over b minus a is equal to negative 1 since we are dividing opposites, like negative 5 divided by positive 5. Here's an example showing how we use the fact that a minus b over b minus a is negative 1. So let's take a look. 64 minus x squared over x squared minus 6x minus 16. Can I cancel the x squareds? No. Both of them are sitting next to either addition or subtraction. Not cancelable. Nothing is cancelable. So we factor. 64 minus x squared, greatest common factor is 1. It is a difference of 2 squares, so we use that formula. 64 came from 8 and 8. X squared came from x and x. 1 plus, 1 minus in either order. Downstairs is a 2 by 2 box factoring. So pause the video if you want to. But ultimately, hopefully, we get x plus 2x minus 8. And then we look at the 2 things that are circled. 8 minus x, x minus 8. Are they carbon copies of each other? No. But they are this brand new pattern. 8 minus x, x minus 8 is this form. A minus b over b minus a. Same thing, but just reversed. Both subtraction. And when you have that, you get to cancel them both off. But they don't quite cancel. They cancel and become negative 1. And so you put a negative 1 instead of one of them. I like to put my negative 1 in the front. You're welcome to put the negative 1 on the top or on the bottom, but not both. If you put negative 1 on top and bottom, they cancel, and you're really putting positive 1, which is not the right thing. So just a single negative 1 either on the top or the bottom, but my preference is in the front. And so there's our final answer. Negative in the front, 8x plus 2 over, 8 plus x over x plus 2. Can we cancel these x's? No, they're both near addition or subtraction. Next page. Can we cancel anything here? X plus 5 over x minus 1. X plus 5 times x minus 1 over x minus 7, 1 plus x. So is this our pattern here, this 1 plus x and this x minus 1? Well, yeah, the x was first and now it's last, and then the 1 was last and now it's first. But there's one important difference, and that's that this is a plus, and that's no good. If this had been right here 1 minus x, then that would be our pattern. X minus 1 over 1 minus x. But with a plus sign there, it is not the pattern. It is never going to be the pattern. 1 plus x cannot possibly be part of that pattern. For example, you could check this by plugging x equals 7. I'm just picking a number into this part of the fraction. And the question is, do we get negative 1? So upstairs, 7 minus 1. Downstairs, 1 plus 7. 6 over 8, not negative 1, right? So you for sure can't just cross them off and put negative 1. Okay, multiplying and dividing algebraic fractions works the same as multiplying and dividing regular numeric fractions. How do we calculate 4 9ths divided by 2 27ths? So here it is. 4/9 divided by 2/27. So you might have seen someplace in a previous math class, in the case of division of two fractions, you copy the first fraction, you change division to multiplication, and you flip over the second fraction. So 2/27 becomes 27/2. Okay, and then in terms of multiplying fractions, you don't need or want a common denominator. We just multiply straight across. But before we do, I strongly encourage you to reduce. So in this case, 27 and 9 are both divisible by 9. So we can replace them by what you get when you divide each of them by 9. It is no problem that the 27 was in the second fraction and the 9 was in the first fraction. After all, when we multiply these, we're just going to make one single fraction with the 4 times 27 upstairs and a 9 times 2 downstairs. So it doesn't matter that they come from different fractions. The 4 and the 2, again, reduce both of those by 2. And so upstairs, we multiply and get 2 times 3 or 6. Downstairs, 1 times 1 or 1. And so the whole answer is just 6. Okay, let's try 11. 15x to the 9y to the third times 2 over 35x to the 4y to the 10. I like both of these to look like fractions, so I'll force this one with an over 1. And then we'll start reducing. 15 and 35 have a common factor of 5. 5 goes in 3 times and 7 times. We have already seen how to reduce x's in cases like this. So x to the 9th over x to the 4th, we know we're supposed to subtract those powers. So we get x to the 5th, and it's upstairs because there were more x's upstairs to start. And then the same deal with y to the 3rd over y to the 10th. Subtract, we get y to the 7th on the bottom because that's where there were more y's to start with. And then we'll just push together everything in the top. 3 times 2, shuffle them together to the front to make 6, x to the 5th, divided by 7, y to the 7. That's it. Okay, part B, definitely tougher. Let's try this one. First thing I'm going to do is recognize this is a division problem. And dividing two fractions, we're going to do that technique that we just did right up above. Copy the first fraction as is. Division becomes multiplication, and you flip the second fraction at that moment. And it might be tempting to cross some things off. I see 2's and 4's and y's all over the place, but none of these things is cancelable yet. Lots of additions and subtractions. We need multiplications, and the way we get multiplications is by factoring. So we'll start with the top left, this first numerator right up here. Greatest common factor is 1, not helpful. Is it a difference of 2 squares? Yes, it is actually. So let's use our difference of 2 squares formula. 4y squared came from 2y and 2y. 1 came from 1 and 1, plus and minus in either order, and that one's done. Downstairs, 4 minus y squared. Greatest common factor is 1. Is it a difference of 2 squares? It is. We're getting a lot of use out of this formula. 4 came from 2 and 2. Y squared came from y and y. 1 plus, 1 minus in either order, times. The other numerator, greatest common factor is y. That's useful. So we pull y out and get a single parentheses. Y minus 2. Downstairs, greatest common factor is 2. Pull that one out. Left with 2y plus 1, and we're done factoring. And now we're looking for things first that are carbon copies of each other, top and bottom. So I see a 2y plus 1 and a 2y plus 1, and they cancel. Now, is there anything else that's a carbon copy top and bottom? And hopefully you say no. But the only other thing to look for is our pattern, where it's the same thing top and bottom, but reverse order and subtraction. And so let's look carefully at this y minus 2 and this 2 minus y and ask ourselves if it's the pattern. Is it the same thing top and bottom? Let's see, y and 2 on the top, 2 and y on the bottom, minus in both, but just reverse order. Yeah, that's exactly our pattern. And so when we see our pattern, we cross them off, and we replace one of them with a negative 1. One, but not both. I like to put that negative in the front of the entire fraction, and then I'll just write what's left. 2y minus 1 on top, y also on top, 2 plus y on the bottom, 2 on the bottom. That's all. You're welcome to distribute upstairs and or downstairs, but there's no need. Factored form in our final answer is perfectly good. Number 12, the last topic in this demo has to do with a fraction being undefined. What happens when you evaluate x plus 4 over x squared minus 25 at x equals 5? Well, let's see. Plug 5 in for all the x's. 5 plus 4 over 5 squared minus 25. 9 over 25 minus 25. Uh-oh. 9 divided by 0. That is undefined. It's not 0. It's not 1. It's undefined. So how do you make a fraction undefined? Well, you make the bottom equal to 0. So let's take a look at 13. For what values of the variable is the fraction 5x over x squared minus x minus 6 undefined? So take the denominator and make it equal 0, because that's going to force this fraction to be undefined. How do you solve that equation equal to 0, that expression equal to 0? Well, it's a quadratic trinomial, 3 terms, 2 by 2 box. So here's the answer you get after you do the 2 by 2 box. Then we set each of the pieces, each of the factors, equal to 0. So x minus 3 is 0, or x plus 2 is 0. And then we solve each of those easier equations for x. Add 3 to the first one, subtract 2 from the second one, we get these two answers. X equals 3 and x equals negative 2 are the values of x that make this fraction right up here undefined. And we could check, we'll just do one of them. Let's do x equals 3. Don't need to check, but I just want to make sure you see what we've done here. If we do x equals 3, upstairs, 5 times 3, downstairs, 3 squared minus 3 minus 6. Upstairs is 15, that actually doesn't matter. Downstairs, 9, what did I do wrong here? Oh, didn't copy the problem right. Minus 6 is what it was supposed to be. 9 minus 3 minus 6. So that is 15 divided by 9 minus 3 minus 6. That's 0. Hey, that's undefined. That's what you've done, is you found the two values of x that make this fraction undefined. Some students balk at the fact that we are ignoring the numerator, right? We only took the denominator and made it equal to 0, and we could have cared less about the numerator. And yeah, that's how you do it. To make a fraction undefined, we could care less about the numerator. Just set the bottom equal to 0.